This is not just a kernel getting bigger. For a fraction of a second, it becomes a pressure vessel, tears itself open, turns much of its inside into foam, and throws that foam into a somersault. But the most obvious explanation for the jump is wrong. Escaping steam does not launch popcorn like a tiny rocket. High-speed experiments found a temporary leg of starch striking the hot surface and kicking the flake into the air. And the familiar pop sound begins before that jump. To see how one snack produces an explosion, a spring, and a sound in one fast sequence, start with the hardware hidden inside the yellow shell. A popcorn kernel has a hard outer hull called the pericarp. Inside is dense starch and a small amount of water. The hull matters because it is strong and relatively good at holding that water in. As the kernel heats past the normal boiling point of water, some moisture becomes vapor, but it cannot freely escape. Pressure rises like it does inside a pressure cooker. In the experiment behind this video, each kernel contained about 20 milligrams of water, yet less than 1 milligram needed to be vapor immediately before rupture. Most of the water could remain liquid while a small vapor fraction created the pressure that loaded the shell. The transition is surprisingly sharp. Researchers heated 50 kernels at controlled oven temperatures. At 170 degrees Celsius, only 17 popped. At 180 degrees, 48 popped. Their pressure vessel model estimated that the hull fails when the internal pressure reaches roughly 10 bar, an order of magnitude figure rather than a universal reading for every kernel. Heat is doing two jobs at once. It increases the vapor pressure, and it softens the starch inside. The kernel is therefore preparing both the force that will break the hull and the material that will expand when that force is suddenly released. A cracked hull or unsuitable moisture can interrupt that sequence before a full pop develops. When the hull finally fractures, the pressure collapses. Water flashes outward as vapor and the hot starch expands into the white, spongy structure we eat. The change looks enormous because the new structure contains much more space. In the same study, average radius grew from about 3.1 millimeters to 6.5, while average density fell to roughly 1/8 of its original value. Popcorn is not simply an inflated yellow kernel. It is closer to a rapidly formed starch foam that has turned itself partly inside out. That explains the volume, but it still does not explain the leap. For that, the researchers recorded a kernel at 2,900 frames per second. The slow-motion sequence separated events that our eyes blend together. First, the hull opened and starch began expanding. Then a narrow leg of starch formed underneath the kernel and pressed against the hot plate. As that leg straightened, it pushed on the surface and launched the changing flake upward. The researchers saw no movement during the initial vapor ejection, so the jump did not behave like rocket thrust. Mechanically, the kernel acts more like a tiny animal using a springy leg. The result can include horizontal motion, vertical motion, and rotation, which is why a piece of popcorn can perform a complete-looking somersault before landing in the pan. The sound has its own timing. With a microphone synchronized to high-speed video, the researchers found that the pop began after fracture started but before the kernel jumped. That rules out the landing or rebound as the main source. They proposed that the sudden release of pressurized water vapor excites changing cavities inside the popcorn, like a tiny resonator. The sound lasted only about 50 milliseconds while the structure was still transforming. So one pop is really a chain. Trapped moisture loads the hull fractures near a critical condition, starch expands into foam, a temporary leg launches the flake, and vapor release produces the sound. Why it spiked will keep using real footage to uncover systems hiding inside ordinary moments. Subscribe for the next one.